So let me briefly run this application. So I have here, I built a little calculator. I add 1 plus 2. And when running this, I expect 3, but okay, we got 2. So that's not what I expected. So let me briefly check my code coverage, how that looks. So there is my the coverage of my calculator. It's all 100%. So, okay, it looks, everything is covered, every branch, that looks good. So, do we need another tool in our toolbox which could unmask such an issue? Well, perhaps mutation testing. So, hello, thank you very much for joining. I will now talk about to let none survive. So how to test our unit tests with mutation testing. My name is Stefan Pölz. I love clean C# code and test-driven .NET development, and have for like about 2 years I now experiment with a lot of CI/CD pipelines. And while that, I have discovered mutation testing for me and what it can do for me. And I would like to share what I have gained so far on knowledge. So we want to tackle today now the what's, the why's, the when we want to use mutation testing, or perhaps when not to use mutation testing, and how mutation testing is working. And we have a brief look into the internals of how such a tool could look like. So what is mutation testing? Mutation testing is a technique which introduces isolated modifications to our source code. For example, it exchanges a plus expression or an add expression to a subtract expression, or negates a Boolean expression. And each little modification is called a mutant. So then the tool scans our source code, and for each mutable expression the tool finds, it will create a mutated version of that code, but only one at a time. So mutants will not be combined, they will be all isolated. And then for each mutant that we have, we then run our entire test suite against that mutant. And now we want at least one test to fail. This is when a failing test is good, because that means that we changed our production code, and indeed, at least one test not only just covered this line of code, but also had an assertion statement in place, which now failed. And indeed now actively defending against a change here, or actively confirming that this code here is indeed necessary. However, if we, with mutation testing, have no failing test, 100% test pass, this is bad, because that means now a mutant has survived. So some code is not asserted, or even perhaps not covered at all. And at the end of a mutation test run, we then get a report which lists the percentage of killed mutants. And this then gives us a view of how effective our test suite is. And the motto of mutation testing is we need to kill all the mutants. So why would this be interesting in the toolbox of a developer? So for me, it really supports test-driven development. It does not replace it at all, but it really, really supports it. And this now brings me to the question, so what is now the difference between the report of a code coverage result and the test effectiveness of a mutation coverage, of a mutation test result? So the benefits of code coverage is super fast. And it really enables a test-driven development cycle with the red-green, with the red-green refactoring phase. And there is plenty of tools which enable this really nicely. There is, for example, Visual Studio Enterprise has live unit testing. There is a Visual Studio extension called nCrunch that I used some time ago. And I now switch to the continuous testing plus cover new and outdated tests of Rider, which basically, I can briefly show this, which briefly then shows in the gutter here. Oops, shows in the gutter. If the test has 1, so currently it's gray, so this test run is outdated, and if it would turn red or green, if this line is covered by a failing or passing test respectively. And we could then run all the impacted tests with every key press, or perhaps every save of the file, and get immediate results of is this line covered or not. But we saw that it does have some weaknesses, because it only checks the coverage, if some code has been executed or not. It does not verify if this code has actually some observable result, some observable change in the system, and this change is asserted at some place. And this is where mutation testing comes in. Now, mutation testing is slower than code coverage because it's some sort of a brute force approach. It really finds all the mutants, runs all tests against each mutated source version. And the more code we have, the more mutants we have, and also the more tests we have, the more tests we need to execute per mutant. So this may take some time. So it's slow, but it's very thorough. So it doesn't really integrate into the TDD cycle very well, but perhaps with every commit in the CI system, we could get an additional report on how good the quality of our test is. So how is this working in detail? I have here a little calculator example. So I have at the bottom, I have my test, and here's my production code. And this is the regular flow. I run the test is passed. This is good, because indeed 1 + 2 = 3. Now mutation testing comes along and sees, it doesn't have a look at the test code, it only has a look at the production code. And it sees, okay, what can I mutate here? So mutation testing, for example, could understand, okay, there is an addition. I now change this, I mutate this into a subtraction. Now we created one mutant of our source code. Now we run all our tests against, and we now indeed have a failing test, and this is good. So this mutant has been killed. And now the tool goes on and finds the next mutant, for example, changes subtraction to an addition, or multiplication to a division, and vice versa. It could also change. Here I have a naive method of finding out if this integer we given is indeed a single digit. So it could change the less than or equal to just a less than, or the less than or equal to a greater than, or change the conditional AND operator to a logical conditional OR. And then again, now we created basically 3 mutants, and for each, we in the meantime run all the tests, and at least one test has to fail. So now we explored some mutations on a language level, but the tooling could also understand the library, the framework it's testing. For example, link. So I have here a method which returns true if all numbers in this collection are even. So mutation testing, the very first one, we run the unit test, see, okay, everything is cool. Now we run the mutation tests. Mutation test sees, okay, this is a Boolean expression and could negate this. Or now for example, understand, okay, this is a link expression and could change the all to an any. And now again, we run all the tests and we see one test is failing. The mutant has been killed. And there is quite a lot of available mutators. I will later on show the tool Striker. I will briefly scroll through here to show this is the available mutations that Striker currently can produce in our production source and then execute each test against. For example, changing an empty string to a non-empty string, or also vice versa. Okay, so what we now explored was the source level mutation. So the tool really analyzes our source code, perhaps with Roslyn, and finds expression that it can change, and then runs the test against. So the advantage of this is, since we are operating on a source level, the report then can really precisely give us information about, okay, what was mutated, which line of code was mutated into what line of code, and this helps us really discover, okay, what action we need to take. That action could be that we add a missing test, or perhaps remove this line altogether because it's maybe not even just uncoverable, but perhaps unassertable. So maybe it doesn't really affect our system to our needs. But the disadvantage is it's slow, or theoretically slow, because each and every time for each mutant, the source code needs to be compiled, and then the tests need to be run against. So this takes some time. A faster approach would be a bytecode level mutation. So because that's on a binary level, this is faster, but the resulting report is not as precise. So it's more difficult to really pinpoint which line of code has changed. I will show this just in a minute. So there is another technique. It's called Mutant Schemata or mutation switching. Some tools call it differently. This is basically source code level mutation, but it only creates one single mutation of our source code, but with switches in between. So perhaps a switch with the first one, ID 1, I have in a if statement that mutated source, but all the other mutations are the original code. So the advantage here, we only need to compile it once and then can use the same compilation in memory and run our test again and again, depending on the currently selected mutant. So for example, this is what Striker.net is using. Now I've mentioned Striker.net, what tools are out there? So there is a GitHub page, the Azure Mutation Testing. There is a lot of tools for different technologies, and this page also lists some papers and videos if you want to know more about mutation testing. I currently focus pretty much exclusively on .NET and C#. For example, Striker.net that's currently in pull request will in the future also support F#. And so on. I listed here some other tools, and we will have now a closer look at Striker. And we will also check out Faultify. So Striker is source code level mutation using mutation schemata, and Faultify is on a byte level. So let's explore Striker. Or to be precise, Striker.net, because there is many flavors with Striker, also Scala and JavaScript. So why I initially started to like Striker is because it is available as a global tool, which I then like to install locally, so that this becomes part of the repository, and I can execute it on any machine where I have my repository or also the CI. And Striker has a lot of configuration possibilities, and again, I like to check in this configuration, then have on the CI the same result as I have locally. So speaking of configuration, what could we configure with Striker? I am searching my... Yes. So we can configure different reporters. For example, a JSON reporter, a command line reporter, or an HTML reporter. I like the HTML reporter. I will show this in a second. This gives a really clear result of how stuff could look like and what was mutated. We can ignore several mutations. For example, don't mutate this file, because maybe it doesn't really make sense to mutate this file, or maybe we don't really can test this file. Maybe it's not even something coverable or assertable. So we can ignore like namespaces or files. We can also ignore several styles of mutations. So my test run currently doesn't mutate any logical expressions. And we can ignore methods. What I always ignore are both configure await, because I rarely have a test in place which will fail if I change a configure await false to a configure await true, or vice versa. And I recently started to use debug.assert a lot, especially when it comes to nullable reference types, to help out the compiler discovering what is null and what is not null at which line of code. And since those are debug asserts, I never have really a test in place which would fail. Or I expect this expression to become false in the first place. So I always like to exclude those. So now when we would run, for example, on a FizzBuzz example, the striker mutator result could look like this. So we see we have 11 mutants killed, 1 survived, 1 is not even covered, and we have ignored 3 due to our configuration. So let's see what Striker did. We see here in green, okay, this is a killed mutant, and Striker changed this not null string, not empty string to an empty string. And it went on, and okay, here is now a debug assert that I have. I assert that the numbers here are not null. Now Striker could mutate this not equals to equals, but I ignored this mutant, so this was not executed. Then we have here some logical mutants. For example, it negates this entire expression. And now I see, okay, here is something, here a mutant survived. So changing this non-empty string to an empty string, I had no test in place, which failed. And down there, I even have a line which was not even covered. So here, Striker mutated an empty string to a non-empty string. And this branch I haven't even covered. So mutation testing always does or depending on the tool, but most likely does with the first test run, also a coverage report to see, okay, which test covers what line, to then be able to execute only impacted tests for each mutant to speed up the process. Now, how would a mutation report with faultified, it's the binary tool, would look like? So, for example, I have here a look at a killed mutant, and now it's a little bit more difficult to see what was changed. So we see the entire method here, and it looks different than my original source code because, yeah, it's compiling it back from the binary back to a C# version. So the source code looks a little bit different, and also it's more difficult to discover that we have changed this negative to a remainder operator. So, but both tools deliver us. Then, okay, CBC mutants have been created, some have been killed, some may have survived, and we get here the effectiveness. It's some score of percentage, the effectiveness of our test suite. So now I would like to jump into a little bit more detail, because some time ago, a friend of me told me that I used to say magic a lot. When there was something I didn't fully understand, I said, okay, there is magic going on. And she has hinted me that this is not good. I should always try to understand it, or maybe then if I don't understand, if I cannot explain it, then maybe I haven't understood it. So ever since, I really jump into detail. So now I would like to write our own little mutation test framework to discover why our initial result, our initial test, so why our addition here, 1 + 2, ended up with being 3. So now this example is super constructed. It is very limited. We see a lot of hard-coded paths, but it should illustrate what mutation testing could look like. So first of all, I want to get some source representation, both of the production code and of the test code. I do this then with Roslyn. So a little crash course in Roslyn. Those are then syntax trees. So a syntax tree basically is the representation, or the the codified representation of our source code, of our text, for our C# text. Then I have some sort of compiler. Now the compiler can compile the original code with the original production and the original source code, test code, and it can compile a mutated version of it. So it takes in the original test code, but gets injected a mutated version of the production code. Then we have some sort of runner. Now the runner does an initial test run. The initial test run is very important. So the regular test run, each and every test must be green, because if we have a failing test, then the mutation test doesn't really make sense, because we have a failing test in the first place. We cannot say now, was this test failing in the first place, or is it now failing because of a mutant which has been killed? So we have the initial test run, and the initial test run must pass. If it fails, we write an error. Okay, now there was something, this is bad. The initial test one must be green. We see I use a tool that we will go into more detail in the follow-up talk. And after the initial test run, we then create our mutants. I will go to them in a minute. So then we get a sort of mutants, a collection of mutants. And now we run for each and every mutant, we for each over them, and have here some identifier. This is perhaps something that could be used for mutation schemata. And then run the tests for each and every mutation, where we say, okay, if the test run has failed, now that's good, that's green. Yes, a mutant was killed. If it has not failed, that means it red, some mutant has survived. So let's come to the heart of the mutation framework. Let's see how we can build up our mutations. So I'm having here a C# syntax walker, which is based on a syntax visitor. And I want to see why my test is failing, because indeed, let's have a look at our source code of the calculator. I have the addition, but I do not use the addition, but the multiplication. And we do not have a failing test initially, because I add 2 and 2. So 2 plus 2 and 2 by 2 both equal to 4. So we don't have a failing test. So let's now kill this mutant. So we could go ahead and first of all find so we will now walk every syntax in our production code. We can now find out, okay, is this a binary expression? Node is binary expression syntax. Now, how can we simply, if we're not familiar with the Boston API, I like to use sharplab.io. Let me briefly paste in the source code of the calculator. And we can then switch here to the syntax tree. And now we see the Roslin representation of this code. So we can jump in and see, okay, we have here a namespace declaration. In this namespace declaration, we have a class declaration, our calculator, which has the static keyword. Now our static class has a method declaration, the add method, where the return type is a double. And now let's have a look at the body. And the body is basically a return statement, which consists of the multiply expression. And the multiply expression is basically a binary expression, which has the multiply expression as a kind. So let me exactly codify that. So we find the binary expression. And additionally, we want to check if this binary expression is indeed of kind, syntax kind dot multiplication, multiply expression. Now, we could do this for all, also for add and subtraction and so on, but let's focus on that for now. And now let's create a mutated version of our source code. With that, I usually do with the syntax factory. So we have the syntax factory. This is used to create new nodes. And we want to create a binary expression, which now is of syntax kind addition, the add expression. But we want the left and the right of this binary expression should be the same. So we say the left still is the left, and the binary right is still is the right. So we now created a new binary expression. Basically, we now created what we had before. So whatever the left was, add, so the plus, the whatever the right was before. And so this is now our, I call this first. I have some noise. Is this me? Not sure.
I think so. No one else is coming up as
okay.
Like high up in the list of people.
Do
normally it does this one, someone else.
Okay, so it gets better now. I hope this is
well.
Okay.
If let me mute everyone, then I'll unfortunately that unmutes you. That mutes you as well, but then I'll unmute you.
Okay.
No, 1 sec. And then I will. If you unmute yourself now, it's gone. Cool.
Yes, it's gone. Cool. Thank you very much. So let me also. So this is our add, and I duplicate now this line and do the same. We want to change this multiply into a subtract. Oops. Subtract. Subtract expression. I used to say subtract, and I still stuck with me. So if you had a subtract, and we want to change the multiply expression to a divide expression to have those basic 4. So that's our divide. And down here, I have a little add mutant method, which now basically creates this new tree and adds it to the list of mutations. So let me call this method 3 times with the original and now the mutated version of our code with the add, the subtract, and the divide. Okay, and what happens now if I run this tool? Now it should discover 3 mutants, run the test 3 times, and the result says, "Ooh, we now have a mutant which survived." So on the left side, we see here the original source code, and we change that into the addition, into the subtraction, and the division. So both the subtraction and the division, they were killed. Our test is good, but the multiplication, that one has survived. So now we know, okay, there is indeed something better for our code. So let's go ahead and fix our test. Perhaps let's do a 3 + 2. This should be 5. And now going ahead and execute the tests again, or not the tests, but the mutation framework, which tests the thing as well. So we now see the mutant has still survived. Oh, at least one test is failing. I have a failing test. What did I do? Oh, so yes, my bad. Of course, I haven't fixed the code. So let me now go ahead and fix the production code. Because now, again, I had a failing test, and that means the mutation report becomes pretty much meaningless. And now with the fixed source in place, I'm not sure why it doesn't spit out any information, but it now should basically show that this mutant has also been killed, and everything should be green. Not sure what's going on here. Okay, so that's pretty much mutation testing. So I want to give a little bit of a conclusion for me. The good stuff about mutation testing, it complements my TDD. It gives more meaning to the code coverage report. And yeah, so those are 2 different reports, and both of them have their strength and their weaknesses. And combined, this is really, really powerful to detect bugs or potential dead code as early as possible. And for me, the more general purpose a library is, the more simpler it is for me to apply test-driven mutation testing and make meaning out of the mutation testing report. So the bad things is that pretty much with everything, it is not a suitable metric, a standalone metric. So just the mutation testing alone is only a part of the story. I had some trouble with getting it one with application code, so I haven't got it one with for example, with Blazor yet. But I tried this like half a year ago. I need to try that again. Maybe it's working now. And also with infrastructure as code, this is pretty much very hard to test or have a test suite in the first place and then make meaningful mutants out of that. A bit of a ugly side of the story is what you need to keep in mind, that mutation testing does depend heavily on the available mutators that the tool is offering. So for me, it's quite important to choose a tool which is maintained and is also updating to newer language versions. For example, in one code base, we have changed to the C#9 is not null style of checking for something is not null. And at that time, when we switched, the tool didn't support this this new C#9 feature yet, so couldn't mutate the source code, and we basically lost a couple of mutants. So it depends on the available mutators, and it also depends on the available mutatable statements in the production code. So if this goes in hand, then we have a meaning. Then we can really get a meaningful mutation coverage, mutation test report out of it. And it may be long running, so it isn't really suitable to execute after each and every modification of our source code. So it maybe not within our TTD cycle, but afterwards perhaps let it run with each CI cycle. But again, with a big solution, this could get pretty big. But Striker also has a solution for that. We could, for a pull request, for example, we could only execute all impacted code, or better to say, only mutate, let the tool only mutate all impacted code. So every code which is a diff to the main branch, only that production code is mutated. And for example, on a merge to master or before publishing, we then could do a full test run, which may take several minutes or maybe even somewhat an hour, depending on the size of the project. And with that, I want to thank you very much for staying a while and listening. And I want to thank .NET Oxford for granting me this opportunity, because since the pandemic, I think I only missed one online episode of the .NET Oxford meetup. And I have taken a lot of knowledge out of there, and it feels good to be able to give just a little bit back. So thank you very much for granting me this opportunity. If you have any questions, I would like to either answer them now, or if you have them later, perhaps approach me either on the .NET Oxford Slack channel or via Twitter. Is it DMs or PMs? My messages are open. So, and if you maybe not have a question, but would like to give me some feedback, then I would very much welcome it, because I gave this talk now, I think this is now the 4th time, and I get feedback every time and improve it. And I would love to continue on that path. So thank you very much.
Awesome. Mutation testing and modeling. That was kind of a very cool talk. Nice to throw that in. And I see a fellow Zoomit user as well.
Yes. So I'm not sure when did I start with
it's such a cool
Zoomit. I think I first saw it from Scott Handelman. I'm still rather new to it. I'm always mixing up the arrow, the arrow and the rectangle. But yeah, maybe in a year I'm a fluent Zoomit user.
Well, I remember the rectangle because a rectangle has corners, and it's the control key on the keyboard. So control is in the corner of your keyboard, so that's how I remember
it. This is now how I will remember too. This is great. Thank you very much.
All these silly things. Right, so we're going to have another 5-minute break. So let's call it 1:15, and then we'll do the final talk, which I do apologize is by me. So I will. If anyone wants to grab a drink or anything, and then yeah, we'll start at 1:15. feel free to unmute and just chat in the break. Or don't.
Great talk, Stefan. Very, very cool.
Thank you very much. And also thank you very much, Dan, for actually, it was a tweet where you showed me, or showed many, for that Wider has this continuous testing and code coverage on safe feature. So I'm using this pretty much every other day now. This is vital now. I'm not depending on that.
Well, so in Daniel's talk earlier, on one of his bullet points was about nCrunch, and sadly that's Visual Studio only, and I don't think the Rider continuous testing is quite as good as nCrunch, but it does the same thing, so it's pretty good to have something. But yeah, it'd be nice if something like nCrunch was in Rider.
This was actually at my very first .NET job. We had nCrunch. Everybody got nCrunch, but back at that time, I didn't appreciate it. I was such a noob. I didn't appreciate it. But its nCrunch is that's very powerful. Wow, I think that also outperforms the enterprise Visual Studio Enterprise live testing.
I was just drinking my beer when you said noob, and that really made me drunk.
Oops.
I didn't spray it everywhere on my computer.
Oops, didn't intend.
Love it.
After seeing your talk for the first time around, Stefan, it blew me away. So I had a little play with it, and I did a little talk at work about mutation testing and Striker.net. I was really curious as to how it actually works, because I was like, if it recompiles it for every mutant, that's going to be very time consuming. So I had a little dig into it, and what it looks like it does is like it walks through all your code, and it basically collects all of the mutants and then injects them all in one go. So basically every method is then like a monster switch statement.
Yep.
And it's like a massive global variable that's like the current mutant. And I was just like, my mind was just blown. I was like, it's so clever, but yet so simple. I was just like, yeah, it's very cool.
I also had a look at the source code. That's quite an elaborate repository by now.
Yeah, I just had another look to refresh my memory, and I just got lost. And yeah.
And I've never tried it. It's really cool. How useful is it in practice in terms of catching problems and stuff like that, or is it more sort of feedback? You look at it as a measure, and then you go back and I don't know. In practice, have you found any real bugs with it? Howlers?
Well, I do a lot of TDD, so the more TDD you do, I guess the more bugs you really catch in the first place, because they don't get there in the first place. But for me, mutation testing was really, really, really super helpful when I started with Rostlin a year ago. So I'm now doing analyzers and currently source code generators. And so the tool now mutates my source code and basically explores some other ways. And I had some revelation about which methods to call with the according parameters. And so for me, it was helping me explore and partially understand Roslyn better with a very new API. Yeah.
Cool.
I've caught bugs with it, and the way I like to frame it to people is like test coverage is like a silhouette of your code. It's like this outline of what's been tested, and it's completely binary. It's either either covered or it's not. Whereas mutation testing actually gives you like a grayscale picture of what you're testing. It kind of tells you, okay, I'm covering it, but like, is that code actually doing anything meaningful? Like, am I,
I've seen tests. I've written tests before, and I've gone back and said that's not actually testing anything. It's running the code, but it's not actually testing whether or not I get the result that I want. Like you say, there's some things where you're not asserting it properly, or you've got the code coverage and it's not real.
Meaningful, I think, is the correct term. This is the word I tried to search before, but I didn't find. Yeah, meaningful. That's the description.
Yes. Good.
Stefan, it's great talk. If you had a look into property-based testing, I do wonder like whether mutation testing complements example-based testing, because example-based testing is sort of in essence kind of, it has those problems, right, where if you don't provide enough examples, you might miss some bugs. But I do wonder, I've not used property-based testing, but the example, one of the talks I saw about it covered like the ad, for example, and you couldn't possibly have a bug with it because it covers essentially what ad does. You know, like example being if you swap the two numbers around, the answer's still the same, that kind of thing.
Mm-hmm. Actually, I only know about property testing like since 4 hours or something, because I watched some talk about, I think it was the Scala version of Striker, and there they compared it to property testing. So I need to revisit that. Yeah, I can't answer that now.
I think it's really hard.
I could answer that tomorrow, perhaps.
Yeah, I thought it was really hard to wrap my head around anyway, like property-based testing. It'd be interesting to see how you get on with it.
So is that like the other dimension then? Sorry, is that like, so obviously this is mutating whether it's a good indicator if you've got a test, a quality indicator, like changing the operator, but actually you don't know if your code is going to be, you know, if you divide by 0, that's still, that's not going to work, right? Or the values, there's another dimension there, which is the values. Is that the other aspect to it then? Or that makes sense?
It seems so. Well, actually, I don't think Striker is actually doing it, but mutation testing could also change where pretty much any constant into something else, change a 0-based constant to a non-0-based constant. I guess this could also be covered by mutation testing actually now that you mention it.